Of chapter number 3, example number 2 says that 100 millicoulomb charge is located at the origin. Find the flux passing through the surface. R is equal to 1, phi is equal to and greater than 0, less than and equal to pi. Theta is changing from 0 to pi radian. So the charge is located at the origin, and you see these limits show that we have got a spherical surface, and it's half of the spherical surface. We need to find out, you see, the flux passing through the spherical surface in the outward direction. We know that the differential area of the spherical surface in the direction of the unit vector AR is equal to r square sine theta d theta d phi AR. And as a point charge is located at the origin, so the electric flux density at a radial distance r will be equal to q divided by 4 pi r square AR. We put the value of q in this particular equation. Q is 100 into 10 raised to power minus 3. So we have divided by 4 pi r square AR. And then we calculate the scalar product of these two vectors. These two vectors are in the same direction, so AR dot AR will be equal to 1. If you consider AR dot AR, so AR dot AR will result in 1. So the scalar product d dot ds will give you 100 into 10 raised to power minus 3 by 4 pi into sine theta d phi. Okay, and we want to calculate the flux passing through the spherical surface. So we know that the flux passing through the spherical surface will be equal to the integration of d dot ds. So the integration of d dot ds will give you the flux passing through the spherical surface in the outward direction. So the flux passing through this spherical surface in the outward direction will be equal to 100 into 10 raised to power minus 3 by 4 pi, and then we have the integration of sine theta d theta. The limits for theta are known, 0 and pi are the limits for theta, and then we have the integration of d phi, and you see we know the limits of phi as well. So we know that the integration of sine theta is minus cos theta, and the integration of d phi is phi. So we simplify this particular equation, and the flux passing through this spherical surface in the outward direction will be equal to 50 millicoulomb. We do example number 3. In example number 3, the volume charge density of 4 x z square cos y by 2 coulomb per cubic meter is located in a region defined by y is changing from 0 to 3.14 and x is changing from 0 to 1, while z is changing from 0 to 3. So this is a closed surface, and this closed surface is in the form of a rectangular box. We need to find out, you see, the flux passing through this rectangular box in the outward direction. So we know that the flux passing through this closed surface in the outward direction will be equal to the charge enclosed by the closed surface. So if we calculate the charge enclosed by the closed surface, that will be equal to the flux passing through this closed surface in the outward direction. So we need to integrate rho v dv, and the integration of rho v dv will give you the integration of rho v dv will give you the charge inside this closed surface, and the charge inside this closed surface will be equal to the flux passing through this closed surface in the outward direction. You see, everything is in the rectangular coordinate system, so the differential volume in the rectangular coordinate system is equal to dx, dy, dz. Okay, then we calculate rho v dv. Let us calculate rho v dv. Here is rho v. Here is rho v. So rho v dv will be equal to 4x z square cos y by 2 dx, dy, and dz. So let us integrate it. So the charge enclosed by the closed surface will be equal to the integration of rho v dv. So we integrate rho v dv, and we get the charge enclosed by this closed surface. We have got 4. We integrate x dx, we integrate z square dz, and we integrate cos y by 2 dy. You see, the integration of x dx is x square by 2. The integration of z square dz is z cube by 2, z cube by 3, and the integration of cos y by 2 is 2 sin y by 2. So this is 2, by the way, this is not 3. So the integration of cos y by 2 is 2 sin of y by 2. So we put the limits on the right hand side of this particular equation. So the charge enclosed by the closed surface will be 36 coulomb, and according to Gauss law, the flux passing through this closed surface in the outward direction will be equal to the charge enclosed by the closed surface. So the flux passing through this closed surface in the outward direction will be 36 coulomb. We do example number 4. In example number 4, the volume charge density is given in the cylindrical coordinate system, which is 4 rho z cube millicoulomb per cubic meter. And this volume charge density is located in a cylinder. You see, the cylinder is defined by these limits. Radius of the cylinder is 3 because rho is changing from 0 to 3. Phi is changing from 0 to 2 pi, and the length of the cylinder is 4 meter because z is changing from 0 to 4. So this volume charge density is located in a closed cylinder, and we need to find out the flux passing through this cylinder in the outward direction. So Gauss law states that the electric flux passing through this cylinder in the outward direction will be equal to the charge enclosed by the cylinder, and the charge enclosed by the cylinder can be calculated with the help of this particular integration. We have the integration of rho v rho v dv. So the integration of rho v dv will give you the total charge enclosed by the closed surface, and according to Gauss law, the charge enclosed by the closed surface will be equal to the flux passing through this closed surface in the outward direction. The closed surface is in the form of a cylinder. So as the closed surface is in the form of a cylinder, the differential volume in the cylindrical coordinate system is equal to rho d rho d phi dz. So we calculate rho v dv first, and then we integrate rho v dv, and the integration of rho v dv will give you the charge enclosed by the closed surface. So the charge enclosed by the closed surface will be equal to 4 into 10 raised to power minus 3. We integrate rho square d rho, then z cube dz, and then d phi. You know that the integration of rho square d rho is rho raised to power 3 by 3. The integration of z cube dz is z raised to power 4 by 4, and the integration of d phi is phi. So we simplify the right hand side, and the simplification of right hand side gives you 4 into 10 raised to power minus 3 rho cube by 3 z raised to power 4 by 4, and then we have phi. So we put the limits on the right hand side, and the charge enclosed by the cylinder is 14.4 coulomb. So according to Gauss law, the flux passing through this closed surface in the outward direction will be equal to the charge enclosed by the closed surface. So this will be the charge enclosed by the closed surface, and this will be the flux passing through this closed surface in the outward direction as well. Example number 5. We have been given the volume charge density in the spherical coordinate system, which is r cos square phi millicoulomb per cubic meter. And this volume charge density is located in a region which is defined by these limits. You see r is changing from 0 to 3, phi is changing from 0 to 2 pi, and theta is changing from 0 to pi. If you look at these limits, so basically the charge is uniformly distributed inside a sphere of radius 3. The radius of the sphere is 3 meter. So basically this is a closed surface, and we want to calculate the flux passing through this Gaussian surface in the outward direction. The flux passing through this closed surface in the outward direction. And according to Gauss law, the flux passing through this closed surface in the outward direction will be equal to the charge enclosed by the closed surface. So we need to calculate the charge inside this sphere of radius 3, and according to Gauss law, the charge inside this sphere will be equal to the flux passing through the sphere in the outward direction. So Gauss law states that the charge enclosed by the closed surface will be equal to the flux passing through this closed surface in the outward direction. As everything is in the spherical coordinate system, so the differential volume in the spherical coordinate system is equal to r square sine theta d theta dr d phi. So this is the spherical the differential volume in the spherical coordinate system, and then we calculate rho v dv. We calculate rho v dv first, and then we integrate it, and the integration of rho v dv will give you the charge enclosed by the closed surface. So the integration of rho v dv gives you the charge enclosed by the closed surface. So the flux passing through this closed surface is given by the charge enclosed by the closed surface. So we have 10 raised to power minus 3. We have the integration of r cube dr we have the integration of sine theta and d theta, and we have the integration of cos square phi. I have not integrated, you see the right hand side, so please integrate it. Let me simplify it for you. The integration of r cube will be r raised to power 4 by 4. The integration of sine theta will be minus cos theta, and the integration of cos square phi d phi will be phi by 2. So the integration of the last term will be phi by 2. So please integrate it and put the values on the right hand side, and you guys will get the answer. You guys will get the charge inside the sphere, and the charge enclosed by the closed surface will be equal to the flux passing through this closed surface in the outward direction. We do example number 3.6. Example number 3.6 says that a surface charge density of 100 microcoulomb is located at r is equal to 2. So basically, this is a surface charge, and this surface charge is located at a radius of 2 meter. If the surface charge is located at a radius of 2 meter, it means that the charge is uniformly distributed on the surface of a sphere, and the radius of the sphere is 2. So basically, this radius in the formula will be represented by A, because this is the radius of the source. So basically, we have a surface charge density. We have got a charge on the surface of a sphere, and we want to calculate the electric flux density and the electric field intensity at r is equal to 4. You see, the radius of the source is 2, and the radial distance of the point under observation with respect to the center of the source is 4. So the point is located outside the source. We know that if the point is located outside the source, then the electric flux density outside the spherical charge will be equal to rho s a square by r square into ar. And what is rho s? Rho s is 100 microcoulomb per square meter. So let us put the values. In this particular equation. We have rho s, which is 100 microcoulomb per square meter. A square is 4, r square is 16, and the electric flux density is 25 ar microcoulomb per square meter. Then we calculate the electric field intensity, and we know that the electric field intensity will be equal to d by epsilon naught. As we are in free space, so d by epsilon naught will give you the electric field intensity, and we know that epsilon naught is 8.85 into 10 raised to power minus 12. So we calculate the electric field intensity with the help of this particular equation. We have 25 into 10 raised to power minus 6 into 10 raised to power 12 by 8.85 into AR. So this is the electric field intensity. The electric field intensity at the given point is 2.82 into 10 raised to power 6 AR volt per meter. We do example number 3.7. In example number 3.7, the electric flux density is given in the rectangular coordinate system. This electric flux density is x square yz ax plus x square z ay plus yx az millicoulomb per square meter. We need to calculate the volume charge density. So we will calculate the volume charge density in accordance with the first equation of Maxwell. The first equation of Maxwell says that the divergence of D will be equal to rho V. So we will calculate rho V in accordance with this particular equation. We will calculate the divergence of this vector in the rectangular coordinate system and the divergence of this vector in the rectangular coordinate system will give you rho v. The second part of the question says if this rho v is located inside the closed surface defined by, you see, the closed surface is in the form of a rectangular box, all right, and this charge is located inside this rectangular box. We need to calculate the flux passing through this rectangular box, and we know that the flux passing through this rectangular box in the outward direction will be equal to the charge located inside this rectangular box. So we need to calculate the charge inside this rectangular box, inside this square, and definitely the charge inside this box, this closed box, will be equal to the flux passing through this closed box in the outward direction. Anyhow, let us calculate the divergence of this vector first. So according to the first equation of Maxwell, the divergence of the divergence of the electric flux density will be equal to rho v. So this is how we calculate the divergence in the rectangular coordinate system. We partially differentiate the x component with respect to x, plus we partially differentiate the y component with respect to y, plus we partially differentiate the z component with respect to z. So if you partially differentiate the x component with respect to x, you guys will get 2xyz millicoulomb per cubic meter. The partial derivative with respect to y will be 0, and the partial derivative with respect to z, the partial derivative of the z component with respect to z will be 0. Now we need to calculate the flux passing through the closed surface. So the flux passing through the closed surface will be equal to the charge inside the closed surface. And as you see that rho v is basically equal to the divergence of d, so we will integrate the divergence of d into dv, and this integration will give you the charge inside the closed surface, and the charge inside the closed surface will be equal to the flux passing through this closed surface in the outward direction. So you see, we know that the charge inside the closed surface will be equal to the integration of rho v dv, and the integration of rho v dv will be equal to this particular integration. So basically we use this particular integration which will give you the charge inside the closed surface, and which will give you the flux passing through this closed surface in the outward direction. So we have the flux which will be equal to 10 raised to power minus 3. Then we have the integration of 2x dx into the integration of y dy into the integration of z dz. The limits are known. We know that the integration of x dx is x square by 2. The integration of y dy is y square by 2. The integration of z dz is z square by 2. So there is a charge of 16 into 10 raised to power minus 3 coulomb inside this closed box, and definitely according to Gauss law, the electric flux passing through this closed surface in the outward direction will be equal to the charge inside this closed surface. Thank you so much.